by two techniques developing under their early segment. Yeah, so the first part then will be about Rydberg-atom microwave structure. The second part will be experiments that we do where we do microwave interferometry. Try to compare a single Rydberg-atom in superposition of two different momentum states. Here, this gray region is the niobium nitride. White region that you see the silicon. And here's a this L-shaped experiments what we'll try to do are have beams or bunches of Rydberg atoms fly across the straight section couple the atoms to the microwave field. So ultimately here we try to do some kind of hybrid cavity. At the moment we're not a single photon so the motivation for this goes back to some proposals in the mid-2000s that Peter Rabel and others were involved with. The idea here was, if you think about different quantum signals, some are good for something, others are good for other things, they might be very stable. So the idea is to try to combine different quantum systems to take advantage of the benefit of the favorable aspects. And so in this paper in the mid-2000s, they looked at microwave circuits to other systems. So the idea here is that this is a cartoon picture of microwave waveguide, which is the center gray region here is the center of waveguide. White regions are the insulated gaps, and this outer gray region is the ground. This is like a coaxial cable that just means this is kind of set up like a resonator, so there's some mode here. And this could have, for example, a super fabricated on the surface of the circuit. And the idea would be to have some atoms.
Okay. And so then this superconducting qubit would be embedded in the circuit, and then above the circuit or nearby, you could have some atoms, or at this time we discussed polar molecules in their ground states, and they would couple. So you'd have a microwave transition in the atoms or molecules that would couple to the resonator mode, and then also the same or a similar frequency, a transition in the superconducting qubit. So here the resonator would be like a bus that could transfer quantum information from the superconducting qubit to the atoms or molecules. And the kind of motivations for this are that because the atoms or molecules are in the gas phase, they can have quite long coherence time. So you could think of using them as long coherence time quantum memories, because superconducting qubits, because they're in the solid state, they don't have such long coherence time. So the best are maybe several tens or 100 microseconds. But the atoms or molecules could have coherence times much, much longer than this. And the other is then that the atoms or molecules can have transitions, as well as having microwave transitions, they can have transitions at other frequencies, for example, at some telecom wavelength or some other visible wavelength. So you can think of using them as a medium to convert optical photons that you would use for quantum communication to microwave photons that you might then propagate in these circuits for computation. So this is kind of the general motivation for this. So then from a sort of Rydberg perspective, we think then, I'll show you our resonator is a little bit different designed, but this here is a resonator. So the center conductor is split at this place here and at this place here. So these are capacitive joins and they act as mirrors of the resonator. For the microwaves, this is like a mirror, and this is the other mirror at the other end of the cavity. And the idea here is that we would have a cloud of Rydberg atoms or a single Rydberg atom above the resonator. And if you wanted to implement this maybe as a quantum memory, you could think about using the transition between two Rydberg states at the microwave frequency that's resonant with the resonator frequency. And that would be the qubit transition in this memory. And if you wanted to do maybe optical to microwave photon conversion, you would have this cloud here and excite them from the ground state to the upper of two Rydberg states, and arrange that then the Rydberg transition from the upper state to the lower Rydberg state would be resonant with the cavity and allow the atom to emit into the resonator and then into the circuit. So this is a very hand-wavy version of this. There are more formal analyses of these types of things, but this is just to give you an idea of the kind of goal of this. So then these were some ideas from the sort of mid 2000s and late 2000s. And then the question is, how do you do this, or what are the problems? And the really big problem is about dealing with stray electric fields close to the surfaces of these superconducting circuits. So you have to cool these devices to 4 Kelvin or a bit below 4 Kelvin. Ideally, for the superconducting circuit people, you would cool it to 30 millikelvin, but that at the moment is quite far away to do. And then at these low temperatures, like molecules or atoms will stick on the surfaces, or if there could be a bit of charge buildup in the gaps. And so you can have stray fields that are difficult to deal with, particularly when you come very close to the surface. And there was this paper here about 10 years ago from Joseph Fortag's group, which they were very, in some way, negative about this, that there would be detrimental absorbates. So here they were considering rubidium atoms that stuck on the surface. And when the polarizable rubidium atom sticks on the surface, it makes a little electric dipole moment, and this makes a field around it. And then as another atom sticks, the field changes, and over time, then these fields change a bit in a way that it's very difficult to deal with. They measured some fields, so 30 microns from a copper surface, they saw the fields from these adsorbates could be around about 1 volt per centimeter, which make it difficult to do these kinds of experiments. And this then led to, there were many other works in this area. So I've just summarized some here involving superconducting waveguides. So there was some work in Zurich between Frederick Merkt and Andreas Wallraff's group, looking at Rydberg atoms or measuring electric fields. This color map is a color map of the electric field distribution above a superconducting waveguide. And they, like at a distance of about 1 millimeter, they saw there were fields of 4 or 5 volts per centimeter. So as you go closer, these fields tend to increase with 1 over the square of the distance from the surface, approximately. So they can get very, very large at tens or hundreds of microns. And then there's some experiments from the group of Serge Haroche and Michel Brun in Paris. And they had a superconducting atom chip, and they implemented on this some superconducting microwave waveguides. They also had big problems with fields, and they found that if they just adsorbed lots of rubidium, so they made almost a coating of rubidium on this surface, this kind of, it didn't minimize the fields, but it minimized the variation in the field. So it kind of like stabilized the fields at least. So they did some spectroscopy using microwave propagating along these waveguides to probe Rydberg atoms and interactions between them. And then there's the work of Joseph Fortag's group in Tübingen. So he has atom chips for cold ground state atoms. And he did initially some experiments where he coupled these ground state atoms, the hyperfine transition in the ground state of rubidium, to a microwave transition driven by the microwave field in the superconducting resonator. And then just in the middle of last year, then they've also reported some experiments with Rydberg states, also coupled to this microwave resonator. So these are rubidium Rydberg states. There's one little difference to what we do is, so our experiments, we've always tried to get the fields to 0 and to then have control of the transitions in 0 field. In their experiments, they've had trouble getting to 0 fields, so they've then compromised and now have a big offset or reasonably large offset fields, and that kind of then minimizes variations because they apply this big field and drive transitions between stark states. Okay, so then we've taken a few steps to try to deal with these problems about stray electric fields. So the first is that we decided we should pick an atom that doesn't cause big problems with surface adsorption. So we chose to do these experiments with helium. And so helium has a ground state electric dipole polarizability of about 1 atomic unit, and rubidium is about 300. So this reduces sticking on these cold surfaces. And if sticking does occur, it reduces the fields that are generated because of it. And so this has sort of been beneficial to us in some way. And then we prepare our helium atoms, as I showed you the other day, in this metastable 2s state, so the triplet metastable state. And then we have 2 CW lasers at 389 nanometers and 786 nanometers to get to the Rydberg states. That's kind of our first thing. We choose the atom. And then we have to choose some transitions in the atom at microwave frequencies between the Rydberg states that are not so sensitive to electric fields. So one plan we have is to use transitions between circular Rydberg states. So we make some circular states. We haven't actually used them in these experiments yet. So these will be states, for example, at n equals 55 with L equals 54 and ML is 54. So you can make these using some microwave transitions or by using some method in excitation in crossed electric and magnetic fields. But what we've done so far is to use 2 photon transitions between S Rydberg states. So these are, So this is the 55S triplet Rydberg state here. So it has a quantum defect of about 0.29. And here's the 56S. And we can drive the transition between these in near zero field as a 2 photon transition. And here then the 2 photons are at about 19.5 gigahertz. And so in this 2 photon transition, we can write an effective Rabi frequency that's the product of the Rabi frequency from the initial state to the intermediate state. And here the intermediate state is the nearest P state. So in this case, it's the 55P state. So we're effectively driving a very off-resonant transition from the 55S to the 55P state. That's the first step in the transition. And then the second step you can view as the transition from this off-resonant position of the 55P to the 56S. So you can write then down these 2 Rabi frequencies from the 55S to 55P and then 55P to 56S. And if you divide by twice the detuning from the intermediate state, which is the detuning from this 55P, then you can get an effective Rabi frequency for this 2 photon process. So this is just to give you some ideas. So these transition moments are a couple of thousand atomic units, and the detuning in our case is about 10 gigahertz, which is a bit too large, but it's okay for what we do. And then the reason we like these states is they have similar Stark shifts. So they're not equal, but they're similar enough. So this plot on the bottom here is the 2 photon transition frequency, or the relative 2 photon transition frequency as a function of electric field. And you can see that for fields below about 100 millivolts per centimeter, the Stark shift of this transition is less than a megahertz. So that's where we want to work. We'd like to try to control the fields at least to below 100 millivolts per centimeter. And then we have the Stark shifts on this level below a megahertz. And then, so that's the second thing, we try to choose these transitions that for the moment are good from the point of view of the atoms. And then the other thing is we then try to use resonators that minimize charge buildup. So we've chosen then this quarter wave geometry. So here now is just a zoomed in version of the resonator part of the chip. So you can see there's a gray region, maybe you can't see it, which is the center conductor. And surrounding it on either side, so it looks a bit like this thing at the bottom, there's a center conductor and there's the insulating gaps on the ground plane. And at this end here, the center conductor is attached or is connected to the ground plane. So it's a grounded end. So here the microwave fields, the mode will have a 0 amplitude. And at the other end here, this is open. So here the mode can have a maximum field strength. And this is where then there's capacitive coupling to this microwave waveguide. And the advantage of this geometry is that if charges build up on the center conductor, they can dissipate by this conduction to the ground plane around. So this helps minimize effects of charge buildup. If you use this half wave geometry, then the center conductor isn't attached to anything, so it's kind of floating. You can do something to kind of avoid this a little bit, but it can build up charge and can have some problems. So this was our kind of choice of resonator design. And then just for the technical, so we fabricate these out of niobium nitride that has a critical temperature of around about 12 Kelvin. And then somehow our fabrication process at the moment kind of limits the Q factors that we have, but in principle, we should be able to do better than we're doing. And then, okay, we make this kind of long resonator here, but we operate it really in its 3rd harmonic, which is at this 19.5 gigahertz that we're interested in. So I could only find these set of resonance measurements for a different resonator. So these are measurements of the transmission through the waveguide. And then there's absorption, or it appears as a reduction in transmission when the field couples into the resonator. So here's the fundamental resonance frequency of the resonator, and the 2nd and 3rd harmonic in this case. And the quality factors go down as you increase the harmonic number or the frequency. And this is because in these types of circuits, the losses are greater, typically at higher frequencies. So we have a quality factor of about 3000 at the moment. I think now that we've learned more about this, we can certainly do better, at least by an order of magnitude, but we have to do improved fabrication to do this. And then we take advantage of the fact that the resonance frequencies of these resonators can be tuned a little bit with temperature. So by changing the temperature, say for example, from 3 Kelvin to 5 Kelvin or 5 or 6 Kelvin, we can change the resonance frequency by about 1%. So we then have to find our Rydberg transition frequency that we want, and then we adjust the temperature of the resonator to then match or to be as close as we can to this atomic transition frequency. And then just maybe at some point we were interested in effects of magnetic fields on these resonance frequencies of the resonators. So mostly the field shifts are weak. So for small fields that we would use in our kind of AMO experiments of say up to 10 Gauss or so, the shifts will be on the order of tens of kilohertz typically. Okay, so these are the steps we've kind of taken to do these experiments. And then, okay, we took one other step, which is we didn't do laser cooling, because the problem if you try to do this all together with say ultra cold atoms is you then have all the possibilities of scattered laser light from the cooling process and trapping process. And if you scatter laser light on these superconducting chips, it then destroys the superconducting behavior and can shift the resonance frequencies and things. So at the moment we do experiments with beams, but ultimately in the long term, it's likely that we then have to switch over to laser cooling. But it's possible to laser cool helium, so it's not something we can't evolve from where we are at the moment. So here we have our beam of helium atoms. They're the yellow thing here, and there's a pair of electrodes here where we pass these two lasers for to excite the atoms from this metastable state to the Rydberg state. So here we excite then this 55s Rydberg state. And then the excited atoms fly over this superconducting chip, and they are kind of the axis of propagation is aligned with that straight section of the resonator. And then they can interact with the resonator field. We can control the fields a bit above the resonator. There's some electrodes. There's one here, and there's one on the side near us that we've just taken away for the picture. And then there's a region after this that we can detect the Rydberg states by pulsed electric field ionization. So when the atoms get to here, we pulse a slowly rising voltage on this upper plate, a negative voltage, and this will ionize the Rydberg states and accelerate the electrons through this little hole here and through some holes in these different heat shields out to a microchannel plate detector, which is at room temperature. So the center of this we can cool to a bit less than 3.5 Kelvin, and there's some heat shields at about 4 Kelvin and about 30 Kelvin outside. This is just to show you our detection. So when we do this pulsed electric field to detect, we apply a pulsed voltage to this upper electrode, and it just rises slowly over a few microseconds. And the 56s state ionizes in a weaker field than the 55s. So we see the electrons appearing from the ionization of the 56s first and the 55s second. And this is kind of, we can sometimes do better separation than from this. So we always measure the signal from the two states, and we use this to normalize and determine the populations of the Rydberg states after the interactions with the resonator. So then as a first experiment to see that we can couple the atoms to the resonator field, we excite a bunch of atoms here that's a few millimeters long, and we let it fly over the resonator. And when it's at the position of the resonator, we just pulse a 500 nanosecond microwave pulse into the waveguide, which then injects microwave field into the resonator, and then we can drive this transition. So this is the 55s to 56s, two-photon transition driven by this microwave field injected into the resonator. So we're just scanning the field. And then from this, we know in helium the transition frequencies very well, and then the quantum defects and start shifts. So from this transition frequency here, we know that the transition that we measure is 150 gigahertz, or 150 kilohertz lower than in zero field. So from this we can extract the start shift, and then this is the start shift, and from this we can extract then the magnitude of the stray electric field. So in this case, at a distance of a couple of hundred microns from the surface, in this beginning experiments, the field we cancel to a bit less than 50 millivolts per centimeter. And then, so the resonator frequency shifts with temperature. So these are on the left, some measurements of the resonator resonances. So because we measure them in transmission, there are kind of interference effects, which are related to kind of Fano type profiles. So there's the transmitted wave through the waveguide, and then there's the scattered wave from the field that goes into the resonator. So you get these asymmetric line shapes. But from these, we can extract resonator parameters like frequencies and quality factors. So the curves at the bottom here are really the resonances of the resonator, just as Lorentzians. So if we're driving our transition in the atom at this frequency here, if we change the temperature from this 3.5 Kelvin to 4.3 Kelvin, the resonator resonance frequency shifts over here, and the enhancement in the microwave field reduces by an order of magnitude or so. So if we change the temperature, we should expect to see a change in the amplitude of the signal from the Rydberg states as we drive the same transition. So this is what we see. So this is the kind of on resonance case here when the resonator frequency matches the Rydberg transition frequency. And this is then this off resonance case here where we've detuned the resonator by adjusting the temperature. And we do some calculations, which maybe are very hard to see there. So there's these dashed red curves, which are calculations where we've measured the resonator resonances, and we can use the relative field strengths that we can determine from this to calculate what we would expect as these changes in signal strengths. So then, okay, with this resonator, we have to be careful because we're operating it in its third harmonic. So if I plot something, this is kind of schematic, it's the microwave field distribution in the mode that we're using. So there's a field strength maximum here, and another maximum here, and then there's a maximum here at the coupling place. So as the atoms are flying along here, we need to think about where they are when we pulse the microwaves or where we let them interact with the field. So they should be at this place here if we want to have a strong interaction. If they're at this place in the middle, we won't see very much effect. So we've done some test experiments where we have a bunch of atoms fly across here, and we inject pulses of microwaves into the resonator, but at different times after we prepare the atoms. So if the atoms haven't reached the resonator yet, this is at these early times here, we don't see any population transfer. So this is the population transfer from the 55S to the 56S state. But if they're at the position of this first field maximum, then we see some significant population transfer. And then we can sort of resolve this minimum of field in this mode in the middle here. And then we see the second maximum here. There's a little bit of distortion here. So we think that maybe there's something stuck or frozen on the resonator that maybe modifies a little bit the field distribution here. But at these frequencies, there's also effects of the reflected microwave fields from the electrodes around that modify the field. We're kind of in the near field of the resonator, but we still have some modifications to the field strength. So there can be elements of this that are difficult to quantify in some way. So the main thing from this is that we aim to then do most of our experiments, say, in one of these maxima. So we try to apply pulses then when the atoms are in one or the other of these fields strength maxima. So then if we do, so we want to look at the coherence of the interaction of the atoms with the resonator field. So to do that, when the atoms are at some position in this first field maximum, we inject a pulse of microwaves, and we just change the length of this pulse, and we can then measure Rabi oscillations. So this is what this is here. So this is the population of the upper Rydberg state as a function of the duration of the microwave pulse that we inject into the resonator. And so we see something here. It's a Rabi frequency of around about 3 megahertz. And then there's a coherence time of about, or in this case, it's around about 800 nanoseconds. And this is at this position in the first mode. And then we can do the same in the second mode. And we maybe because of these slightly different field strength distributions, the coherence time is a little bit reduced. In this case, it's about 400 nanoseconds, and the Rabi frequency is around about the same. But we found in all of these experiments, there are bunches of atoms, they have a size of about a bit less maybe than 100 microns in the dimension above the surface. So because they're flying above this field distribution that's very inhomogeneous, there are some that are close to the surface that see a stronger microwave field, and others that are further away and see a weaker microwave field. So a lot of this we think is not really decoherence, it's just dephasing of all these different Rabi frequencies. So in some future plans, we need to now make sort of smaller bunches of atoms that are more tightly localized above the surface. And we think then we should have a longer coherence times in these Rabi interactions. But then we can also look at the coherence times of the atomic superposition states that we prepare. And so we do that by Ramsey spectroscopy. And so the first thing we can do there is we can use some Ramsey spectroscopy technique to use the atoms to probe the kind of spectral response of the resonator. So this may be extremely hard to see. So here we inject 2 microwave pulses into the resonator, separated in time by 100 nanoseconds. So the first pulse, say on resonance, will make a equal superposition state of the 2 Rydberg states. And then there's some free evolution time. And then there's a second pulse that then projects this onto the basis state. So this is the Ramsey approach. And if you do this kind of spectroscopy, then you see these, and scan the frequency, you see then these Ramsey fringes. And so the black points here are the experimental data. And then we can use, okay, so we calculate what this should be for a particular resonance or resonator resonance frequency, because that modifies how the amplitude should be in the spectrum. And then from the spectrum, then we can kind of fit from the calculation to extract what the resonator profile should be. So here, one of these, the dashed curve here is the kind of measured resonator profile that we get from measuring transmission in the waveguide. And the continuous blue curve here is then the fitted one, or the best fit one that we get by using the atoms as the kind of sensor of the field. And here then we can do this. Oh, so the first thing I should say, so, I mean, you see there's reasonably good contrast here. So this tells us that somehow we still have good coherence of the atomic superposition states, at least in this 100 nanoseconds free evolution time. And then we can detune the resonator by adjusting the temperature of the chip. And as we move it off resonance, then the amplitude of these signals reduces. And eventually, if it's kind of far off resonance, we don't see any transfer at all. But that was, so these two pulses separated by 100 nanoseconds, these are when the atoms are within this first field maximum of the mode. So then we can do another experiment where we prepare the initial superposition state or initial interaction when the atoms are in the first maximum, and then let them evolve freely until they get to the second maximum, and then make the second pulse of the Ramsey sequence. And so this gives then a much longer free evolution time, and then also much narrower Ramsey fringes. So this is just a part in the middle of this Ramsey spectrum under these conditions. And so this is just to show you, so we can't, it takes quite a while to measure, so we don't measure many points, but the red is a fit to this. And then you can see that we have still reasonable contrast of 40 or 50% on resonance after this long free evolution time. And from this, we can then tell what the coherence time of the atomic superposition states are, because the atoms now evolved for this 2 microseconds freely. And if there were big inhomogeneities in the stray fields, they would sort of go out of phase, or we'd see a lot of decoherence, so we wouldn't see a good contrast in these Ramsey fringes. So from fitting this is a kind of zoomed in version in the middle of the spectrum. We can fit these amplitude of these fringes after this 2 microsecond evolution time. And we see then that the coherence time of the atomic states must be longer than 2.5 microseconds. And 2.5 microseconds is important because that's the time it takes our atoms, which are moving at 2,000 meters per second, to cross the length of the resonator, which is 5 millimeters. So we're now not actually limited in this kind of coherence time by the atoms or the distribution of atoms, but by their speed as they travel across the resonator. So from this kind of high resolution Ramsey spectroscopy, we see that this 2-photon transition is actually, we've done better field cancellation in these experiments, detuned by about 50 kilohertz from the field-free transition frequency. And in this case, then we've controlled the fields to about 26 or so millivolts per centimeter. And this is at a distance of 300 microns above this 3.8 Kelvin superconducting chip. So that's kind of where we are with this at the moment. So we've seen that we can prepare atoms and let them interact resonantly with this microwave fields in this type of resonator, and we can control the fields close to the surface of this to this range of a few tens of millivolts per centimeter. And our coherence times, at least of the atomic superposition states that we generate, are not limited by the fields, so limited by the flight of the atoms above the resonator. So at the moment, we're still driving these 2-photon transitions. So to get to some interesting regime for cavity QED, we want to get to single photon transitions and then the single photon strong coupling regime. So our plan for that now is to, rather than drive these 2-photon transitions, we want to dress the atom with a microwave field that's a little bit off resonant from this 2-photon transition frequency. And if we do strong dressing, then the atom can absorb the other photon for the transition from the resonator. And that would allow us then to couple this dressed atom to the resonator field as in a single photon coupling in that sense. And then we still would like to get closer to the surface, because then we can have stronger coupling to single photons in the resonator. And so for that, we still need to control fields better, or control the sensitivity of the atoms to fields. So maybe Luke, you might have seen he had a poster where we've been doing some other experiments that are also dressing experiments, where we dress these S states with some P character to kind of reduce their sensitivity to DC electric fields. And this is based on ideas of James Martin's group in Waterloo he published about 10 years ago or so. So we've tried to implement the same ideas in a test experiment with helium, and then we want to move to implementing in this type of apparatus as well. So that's the end of this first part. Maybe I'll answer some questions just to give a break or give you a chance to. So are there any queries? Yeah.
So with the goal ultimately to completely stop the atom above the chip?
Yeah. So you could foresee even having tweezer, like, so you could have arrays of these resonators with arrays of tweezers over them or something like this, and then use the resonators, like tune the atoms in and out of resonance, the resonator as a way to control interactions at longer range. So there's ideas in ion traps to do this type of thing for long range interactions. And that's also, in principle, could be done here. So the problem, I mean, I think now that we know how a lot of this works, we can think about how you would do that. But I mean, there's lots of problems with these superconducting things about scattering optical photons. And so you have to be really careful about this. So we think about maybe integrating some kind of fiber cavity things above the chip or this kind of thing to try to allow us to control that light that we would use for other Rydberg excitation or trapping or things like this as well. Right. Okay, so in this case, the best of the superconducting circuits is that they're really scalable. So I mean, once you make these resonators and work out how to make the ones you want, I mean, you can print lots of them or fabricate lots of them quite easily. And then I would say then there's another advantage that like in superconducting circuit business, I mean, the coupling rates are very high. So to couple a single photon to a superconducting qubit, you can do this at tens or 100 megahertz coupling rate. The problem is the coherence times. So okay, then what really matters is say the ratio of the inverse of the coupling rate to the coherence time. So how many operations can you perform? So the coherence times are tens or hundreds of microseconds, but they're not kind of, they're never going to get to milliseconds because of like phone-on modes and things in these devices. So the idea here is then that the atoms can have similar coupling rates because we've these big transition moments in the Rydberg states, but because they're in the gas phase, they could have then much longer coherence times. And I mean, there's ideas from, for example, Serge Haroche and Michel Brun that you could do these transitions to couple transitions between circular Rydberg states and then engineer the environment above the resonator. So there's no mode for the circular states to decay except into the resonator. And they think that you could have hours coherence time. I find it's a little bit optimistic, or maybe more than a little bit, but at least it's a good dream to have. So you would sort of engineer the electromagnetic environment to give you this long or small chance of spontaneous emission, and then have these couples into the mode you want in the resonator. So that's the band. The problem with the atoms is about scalability. So that's the disadvantage. So, is there anything else? Okay, so then I go on to the very last thing, which is a little bit different, but also it uses helium. So in my lab, we do a lot of things with helium, and that was all based on this superconducting circuit thing. So that's why we've ended up with helium. So then the last part is then about these matter wave interferometry experiments. And so the idea here is that we want to have a single Rydberg atom, and this is just extremely schematic, but you can think about it sort of de Broglie wave packet associated with the atom. And we want to do something that separates the atom into two spatially separated momentum states. So you can then think of a de Broglie wave packet that's moved a little to the left and a little to the right. And then in principle, these should interfere with each other. So we could see some effect of interference. In reality, all of these interference effects have influence on the phase of the internal state. So we actually measure the internal state populations, but they tell us something about the de Broglie phase or the matter wave phase. Okay, so this is kind of the idea of what we want to do. And I just put this in a little bit of context briefly. So there's the thing that this is closest to is Slem-Gerlach interferometry. So this was something, so in the mid-90s, there were several atom interferometry experiments that kind of all produced results at the same time. So there were these light pulse interferometry experiments from Steve Chu's group. And then there was this magnetic interferometry experiment by his group in Paris. And then there was this grating interferometry with atoms passing through micro or nanofabricated gratings in constants, and also I think Dave Pritchard's group in MIT. So at around this time, then one way to do this type of thing is to prepare hydrogen atoms in a superposition of spin states and let them fly through an inhomogeneous magnetic field. And then the two spin components see different forces in the magnetic field, and this leads to a spatial separation of these atomic wave packets. And this is some effective interference they see from measuring the populations of the states, which reflects this matter wave interference. And then there are these grating interferometers. So these now, there's Marcus Arndt and Anton Zeilinger in Vienna do experiments that have gone to bigger and bigger molecules in this direction. And they're mostly interested in heavy molecules to look at when do wave functions collapse when you have such very large masses. So they talk about big, the size is a few nanometers, but the masses are very, very big. So they can be thousands or tens of thousands of atomic units. And these are experiments where these beams of molecules are passed through nanofabricated gratings, and they can look at interference patterns. And then there are the light pulse interferometers that the people that do, so like Mark Kasevich and originally Steve Chu, and we were talking earlier about Holger Muller, So they laser cool ground state atoms and then use a pulse of laser light that drives a Raman transition to give a momentum kick and generate a superposition at the same time. So the atoms then are ended up after this momentum kick in a superposition of 2 different momentum states and 2 different internal states. And from this, you can do extremely precise gravity measurements and measurements of the fine structure constant and many other things like this. So what we are doing then is an electric version of this Slem-Gerlach interferometry, and we do it with atoms then in Rydberg states. And the kind of neat aspect, so there's some motivation for this, which I'll tell you on the following slide, but some neat aspect of it, I mean, the atoms are really big. So they're the biggest atoms that matter wave interferometry has been observed for. So they're, if you take the size of the Rydberg electron charge distribution, so at n equals 55, this is around about 500 nanometers. Then they're kind of a few orders of magnitude bigger than any other objects that have been interfered. They're not heavier, certainly, but the de Broglie wavelengths are small, so like 50 picometers or so, whereas the laser-cooled ultra-cold atoms have de Broglie wavelengths of a few tens of nanometers. But the other thing is that we have these very big electric dipole moments. So this is interesting for some fundamental kind of things. So having these big dipole moments, you can look at topological phases. So there's this Aronoff-Bowman phase. That's for that's a kind of interference of, or it's a quantum phase that's accumulated for an electron moving in a magnetic field, so moving in 2 ways around a magnetic field line. And there's an analog of this for an electric dipole moving in around a magnetic field line. This is called a He-Mikeller-Wilkins phase. And there have been previous measurements of this with ground state atoms that have tested it or seen phase shifts of a few tens of milliradians. But we can, we've actually done some experiments in this area already. We can see phase shifts of many pi radians. So we can really take advantage of the big dipole moments of the Rydberg states to test this kind of geometric phase effects. And then with my colleague David Cassidy, so he does experiments with positronium atoms. So this is an electron bound to a positron. And with him, we would like to try to measure gravity for antimatter. So our take on this is we try to measure gravity for positronium. So we try to measure the acceleration of positronium in the Earth's gravitational field. And the advantage of positronium, or one advantage over antihydrogen, is that we can do this in a lab in our building, in our department. And we have about 1 million positronium atoms per second. Whereas if you want to do this with antihydrogen, you do it at CERN, and you have a few months in the year to do this, and you have a couple of antihydrogen atoms each cycle every few minutes of the experiment to do. So there's trade-offs. I mean, we have now half matter, half antimatter, so it makes the experiment different, but we can repeat it a bit more often. So maybe there's some advantage there. But then the thing with positronium, so in the ground state, the triplet ground state is the longer lived one. It lives for 140 nanoseconds, and that's not really long enough to be sensitive to gravity. So you couldn't really do ground state atom interferometry. So, but when we excite it to Rydberg states, so once you go above n equals 2, then spontaneous emission dominates the annihilation for every other state. So once you go above the 2s state, all other states will decay first to the ground state by spontaneous emission before annihilating. And this is because of this reduced overlap of the electron and positron wave functions. So these are measurements we've made of the lifetimes of Rydberg states in positronium. This is up to about n equals 20. And you can see we can measure lifetimes of 20 or 30 microseconds. And these are the lifetimes of the Elmech Stark states that I talked about in hydrogen. So they're nothing surprising about this. It's just that we can see that we can measure them with these longer lifetimes. And this is kind of long enough to do a gravity measurement. So if you can measure, if you can probe gravity for about 10 or 20 microseconds, you can get to 10% precision by a kind of interferometry technique. And then at the end, I'll just mention something about a connection with cold chemistry, just from the, given the subject of the meeting. So, okay, so how do we do this? So I showed you the other day that if we want to decelerate atoms in these Rydberg states, we want to prepare a bunch of them in a state like this blue state here. So when the atom in this state moves from a weak field to a strong field, it gains internal energy and it'll lose kinetic energy. So to do this interferometry, we try to generate a superposition of 2 of these states. So we prepare one atom in a superposition of 2 of these states which have different Stark shifts. And then when this atom moves from a weak field into a strong field, the 2 components see different forces. And then this leads to a spatial separation of the 2 momentum components. So we do this in a kind of, we do it with helium, and we do it in this kind of simplified experiment here. So we have the beam of helium flying along here. And in this place here is where the interferometer is. So we have this wedge-shaped pair of electrodes. They're closer together. At this end, this is about 1 centimeter, and at this end here, they're about 3 centimeters apart. And then we first excite the atoms to in this case, the 56S Rydberg state. And then we apply a sequence of microwave pulses and a sequence of electric field pulses to apply these forces to generate the momentum state superpositions. And then after we do this, we then can detect the states or measure them, the populations of the two Rydberg states, which tell us then that's how we measure the interference patterns. So here we also use a two-photon transition, but this happens to be from the 56S to 57S. This was for some microwave, I don't know, the microwave field strength was better in this apparatus for this slightly lower frequency. So this transition occurs at 18.5 gigahertz, and for fields up to about 2.8 volts per centimeter, which is where this avoided crossing is here, we can then turn on and off the field without ending up with population going into any other Rydberg states. So how the scheme works is that we first prepare the atoms in the lower of the two Rydberg states, and then so that's with laser excitation, and then we apply a microwave pulse to make a equal superposition of the two states. We apply pi over 2 pulses of microwaves. And then after that, we then pulse on some voltage on one of these wedge-shaped electrodes, and this makes this inhomogeneous electric field. And so this moves the atom into this strong field here. And in here, so it's come off, but I've plotted here, then these are the induced electric dipole moments of the two states. So they're slightly different to each other. And this bottom plot, which you can't see at all. So this is the difference between the two dipole moments. So they're around about 400 dBi difference in this field here. So this is what gives then a difference in the force, because the force depends on the induced dipole moment. And so for these different dipole moments, we get a different force on the two states, on the components in these two states. So now after this gradient pulse here, now we've got these two components that are moving now at different speeds, and they've also accumulated, well, different Stark phase shifts. So what we do then is we apply a pi pulse. So that inverts the internal state population. So we've turned off the electric field gradient pulse, and now we've inverted the internal states, and then we apply the same electric field gradient pulse again. And so what this pi pulse does, this is now an echo sequence. And so the Stark shift, or the phase accumulated by the superposition that's associated with the Stark shift, cancels from the phase accumulated in the second pulse to the one in the first. So we're left with then phase shifts because of other things. One of these is the motion and the separation between the wave packets. So then finally we turn off this pulse and we apply a final pi over 2 pulse to project whatever the superposition state is onto our basis, and then we measure the populations of the two Rydberg states then down at this detection region. So if we do this, this is just to show you the kind of scales of what's going on here. So for about half a microsecond, or a couple of hundred nanoseconds, we apply this first gradient pulse. So that's after preparing the superposition. And then the two components have slightly different speeds. So they're different by 0.2 or so millimeters per second. And at this time, so then we wait while this two wave packets expand. So we wait about 5 microseconds. And after that time, they've expanded by about a nanometer or so. So we've got these two wave packets that are separated by a nanometer. And that's still much smaller than the electron charge distribution, which is a few hundred nanometers. But it's still, we still separated the center of mass in this case. And then the final pulse, the gradient pulse, or sorry, the final gradient pulse we apply here, this brings the two components back to the same speed. And then they propagate with a kind of constant separation. And then what we're looking for, if you want to think in this de Broglie wave picture, then at this point here, the red wave packet has been shifted by some amount upwards, and the blue wave packet has been shifted by some amount downwards. And we're measuring something that reflects interference between these two wave packets. So in principle, we can move the wave packets in and out of phase with each other and see fringes appear and disappear. But if we were to look at the atoms. So this is then what we measure. So this is the population of the upper Rydberg state. So we just choose this. We could choose either of the states to detect. And 0 here is the kind of no field gradient applied. And then as we turn on, so here what we're scanning is the amplitude of the voltage pulses we apply to generate these gradients. So we're really scanning the force that we apply to the atoms. And we see then that we start to see these fringes as we increase the amplitude of these fields. And these fringes build up more quickly as the amplitude goes on. This is because of the quadratic Stark shift of the states. And in principle, this interference pattern should be symmetric, about 0, but it's not, because this thing now is very sensitive to field gradients. And in our experiments, we put a lot of effort to cancel fields. So we cancel very well the average field that the atoms see, but that's not the same as canceling the field gradient that they see. So there's just a small residual gradient that we didn't cancel, or we don't cancel by canceling the field, that leads to this offset here of the center of the interference pattern. And so otherwise the thing is symmetric then about this offset gradient. And then we want to calculate something to see that we know what's going on. So here then we calculate the evolution of the states that we prepare. So we can separate this into the two arms basically of the interferometer. So this P1 is the momentum in arm 1. So this will be the arm that might be the 56S state initially, and then switches over after some time. And then here there's a phase associated with the propagation in arm 2. And these fringes that we see here then are the phase differences between these two components. And these have some different contributions. So there's a contribution associated with the action in each of the classical paths, or the classical action. And there's also a contribution associated with the separation between the wave packets at the end, because this is an interferometer where we just separate the wave packets. We don't bring them back together. In principle, we could, but at the moment we just separate them. And so this is the same, or it's essentially analogous to what one sees in these light pulse interferometers. And then this action, the phase, so this is the integral of the Lagrangian. So there's a dynamic part that's to do with the kinetic energies in each of the arms. And then there's a potential energy part, which is for us to do with the Stark shifts in each arm. And this actually isn't zero. So we apply this echo sequence, which mostly cancels the Stark phase, but because the atoms are flying in this field gradient, at the beginning of their flight, the field's a little bit bigger than at the end of their flight. So they actually accumulate a bit more Stark phase in the first electric field gradient pulse than they do in the second. So this leads to a little phase shift that we have to consider or include in these calculations. Okay. And so then there's this phase that's to do with the separation. And this is the one that if the change in momentum is small compared to the initial momentum, this then depends on the de Broglie wavelength. So this separation phase then is the one you would connect to the de Broglie waves interfering if you wanted to do this. But we have to think this, so that is contributing here, but there's also these contributions from these other phase shifts that we have to think about. And so if we do this, then we get this red curve here, and all we include here is the velocity spread of the atoms, and this is what gives this decoherence as we go to bigger spatial separations. So, and then, okay, the thing we can extract from this then is that from the calculations, we see that we can see fringes for spatial separations of about 1 nanometer in this case. Okay, and then so you can determine something to do with the coherence length if you've got a velocity distribution in a beam like this. And so the longitudinal coherence length, which is what we care about, is the h bar divided by the sigma of the velocity spread. And so this is about 0.4 nanometers, which agrees kind of with what we would expect from the reduction in the amplitude of these fringes. So the 1/e separation is something like this 0.4 nanometers. And in this case, it's limited by the velocity spread completely. So, okay, I was going to summarize, but so, okay, so the main conclusion from this is that in this longitudinal configuration, the kind of contrast we can see as we separate the wave packets is limited by this velocity distribution. We've now also done some test experiments in a transverse configuration where the velocity spread is much, much smaller. And then we can see reasonable contrast fringes up to about 10 nanometers separation. And now we have some limitations on fields, and that I think we can overcome some of these. So I think we can get to tens of nanometers, maybe 100 nanometers. And that then starts to be on the size of the Rydberg electron charge distribution. So then we could think about having these two wave packets that are separated by the size of the Rydberg electron charge distribution. But then there's a little connection to this cold chemistry. So what we would like to do with this is, or one of the things as well as these gravity measurements with positronium, is we would like to do connected to these resonant energy transfer experiments I mentioned the other day. So we would like to do this in a way that in one of the arms of the interferometer, we can apply a field that brings one of the states into resonance with the resonant energy transfer or the dipole-dipole interaction with the ammonia molecules. And there, if we can control orientation, we'd like to look at how, if we can extract directly from the phase shifts of these matter wave interference patterns, we think we can maybe extract the cross sections for these processes. So it'd be a kind of direct kind of phase shift measurement of this. But we'd also like to look at effects of decoherence. So when this interaction occurs at long range, the coherence should be preserved, or to some extent, to some amount of time. But if the ammonia molecule gets inside the Rydberg electron charge distribution and interacts with the ion, then we think maybe decoherence will be faster for the interaction or something like this. So we want to try to understand what kinds of chemical processes lead to faster decoherence or slower decoherence. So this is kind of what we think about in the directions we're interested in going. And this is kind of nice. We have this kind of simple, kind of controllable system to look at these effects. So this is the end. So I've shown you that we can make these matter wave interferometer with Rydberg atoms, and we can separate the wave packets at the moment by about a nanometer and still see fringes. And if we do this transverse experiment, we can get to about 10 nanometers. And here the atoms are big, so they're 500 nanometer size. So I think they're the biggest things that have ever been interfered in this matter wave kind of way. And the induced electrodynamos are really, really big. So this is kind of one of the appeals of some of these kinds of experiments. So this work is done by James Palmer. He was a PhD student that worked on this, and Jake Tommy has then done all of this work to do with the phase shifts. I should say, I didn't say at the end of the first part, so the superconducting circuit thing. So Luke Brown and Dan Walker are here. So they're the students working on the superconducting circuit experiments at the moment. And previously there was a student, Alex Morgan, who had built that experiment in the beginning for his PhD. So I finished there, and thank you for your attention. Yeah. Yeah, okay. Yeah, so there's some little fringes. Yeah. Sorry. So the question is that in this data here, there's some little faster oscillations, some other kind of smaller fringes. So a lot of this relies on having as similar duration and a similar amplitude electric field pulses for the two pulses. So even, I mean, the pulses are about 100 or a couple of hundred nanoseconds long, but if they differ by a nanosecond, then we don't cancel enough of the Stark phase. And these are then, they're extra phase accumulated by the Stark shifts that are a little bit different for the two. So this is a bit of a challenge with this, which we hadn't realized in the beginning. I mean, we have to really control the pulse lengths very well. And the way we generate the pulses, they have to really match both of them. So that's, yeah, so if we don't do this well, there's even more of these faster oscillations, which are all to do with Stark shift and accumulation of these big fast phase accumulations. Like maybe it's time to eat something. I think it's time to eat something. But maybe before we stop, just as it's the last talk, so I'm sure all of you with me would like to thank Hussein. I mean, so Hussein was very insistent that this should be in person. And I think from all of the discussions we've had also with him, I mean, it's been really great to come to something in person in such an environment that, I mean, it's made me realize that the Zoom business is not the future. I mean, the future is really getting back to meeting with each other and discussing things. So maybe we can just together thank Hussein for all these things.
All of the lecturers today, in fact, the whole week, because you know, as with any other school, it's a sort of a tension between what the students want and what the lecturers wish to deliver. And of course, next week we receive a survey about your impression of the school, of course, honest. I think you agree with me in a large part, especially because of this gathering. It's been a great success. Because of you, because of all of the lecturers who are here or have left. I have, this is part of my view too, but I really enjoy the connect. All of the lectures also on the ITAMP YouTube channel, playlist and stuff. But I also like to emphasize this: if any of us will sort of design a course, special course on contemporary topics, material discovered equivalent of a half semester. The number of hours that you have spent, everybody else has spent here is lot of material to digest, but I hope that you have made the connections here. You have learned something, and at the same time, you have also enjoyed the atmosphere. We're not going to end. Lunches will be served, and dinner will be as usual. As far as I know, most of us are staying today. Okay, some of us are departing tomorrow, and the rest perhaps Sunday morning. But as I mentioned, breakfast will be early tomorrow because there are a number of people who are leaving us. So it will be, I think, around 7:50-ish or so for breakfast, in case we get up earlier. But otherwise, today will be as around the whole time. So without much further ado, and thank to all, Stephen and everybody else. So let's go for lunch.